about structure of protons and nuclei at small x.
Okay. Thanks for having me, and thanks for having the last talk. And today I will talk about exercising structure of proton and nuclear at small x, at the mainly focus on the future EIC collider. And I'm Wenbin Zhao. I'm a postdoc in Wayne State University and the Brookhaven National Lab. I would like to give the credits to my collaborators, who are Heike, Liang Shinki, and Shen Shen. Okay, let me start with the higher dynamic response. In high-ion collisions, there is a quark-gluon plasma, and one of the important signature of the quark-gluon plasma is the collective flow. And in the high-ion community, the standard model to describe the collectivity is the higher dynamic evolutions. In the higher dynamic evolutions, for example, this is initial state entropy profile or initial state energy density profile after the collision of two high-ion collisions, and after the higher dynamics evolutions, they translate the initial state anisotropies to the final state momentums. In other words, you can get for the momentum distributions of final state particles, and then do the Fourier decompositions. You can get different flow harmonics, such as input flow, triangle flow, and also V4, V5. That is, the higher dynamics translates initial state anisotropies to the final state momentum anisotropies. And this plot shows the collectivity in small system. Recently, the small systems such as proton lab, and the D-gold, hemispheric gold. In such small systems, people also observe the non-trivial collective features, which is similar to heavy-ion collisions. And this is the Alice estimate of the VT2 in periodic collisions as a function of multiplicity. And there is two lines from the higher dynamic simulations. The black line means assume the proton has the substructure fluctuations, and the red line means assume that the proton is a round proton or do not have enough geometry fluctuations. And then with this initial state input and run the higher dynamic evolutions, you can see that with the proton with the substructure fluctuations can describe the collective features in periodic collisions well, but without the substructure fluctuations, or assume the proton is roughly round, so they cannot get enough initial state fluctuations and cannot describe get enough V2 compared to the Alice data.
Sorry?
Yeah.
Sorry, what is mu2 or V2?
V2 means, for example, when you observe the final momentum distribution of particles, and then you do the Fourier decomposition of this momentum distribution, and the V2 is the full decomposition coefficients of the second hand, this is the third hand, and this means the elliptic flow, means this shape. Yeah, in the momentum space, and this is energy distribution in the coordinate space or entropy distribution, and the higher dynamics translate initial state correlation in the coordinate space to the momentum space.
Yes, in fact, the standard plot has probably been shown like in every single talk the last 4 weeks, I suppose.
Yeah, before this week,
So
but never this week.
This week, this is the
So
only
you missed
one.
it all. You would have seen it 50 times.
Yeah, that's fine.
Yeah,
I mean, this right plot is
That's
also
really all
coordinate
that we're-
space, right? So it's a
Yeah.
little,
Yeah.
they're both
This
coordinate
week
space.
was-
Yeah, this just to emphasize the initial geometry, proton, or initial geometry of nucleus is the important input for our higher dynamic evolution. Yeah, that's why we show the nuclear structure to give our input. And then I go to the diffractive result. This is a diffractive in optics. For example, this is a plane wave travel forward and meet obstacle or aperture with a size of r, and then the diffractive process. And then go to a screen or detector, we can observe very beautiful diffractive patterns. For example, with a maximum at the central of the and there is a minimum and second maximum and third and second minimum. For example, this is the different patterns taken from wiki of the in optics. if we translate these distributions from the coordinate space to the momentum space, then in the momentum space, the position of the minimum and the maximum of the diffract pattern are determined by the target size only. In other words, we can get the information of the target size by the diffractive patterns, even similar in optics or in Hamilton equations. And then now using the same idea from the optics, we use constraint. First, we constrain the fluctuation proton geometry from the DRS for diffractive process. This is a very famous. This picture had talked about a lot in the previous talks. This is the diffractive vector meson production process in the high energy collisions. First is the virtual photon split to the QQ bar pair. Since the lifetime of QQ bar pair is much larger than the time scale interactions, so we can separate this process into several stages, or we can do the high energy factorizations. First is the virtual photon split to QQ bar pair with a wave function psi gamma. This is a pure QED process. And then the QQ bar dipole scatter with a target elastically. And then after scattering, the QQ bar dipole will recombine into the chip side with a wave function psi v. And since this is a diffractive process, we only have the final state chip side, which is a color neutral state, and the initial state is also color neutral state. So there is no net color transfer between this dipole object and the target. And in the framework of the diffractive scattering amplitude, and we assuming the factorization process, we can get the diffractive scattering amplitude by this formula. This is the whole diffractive process, which is proportional to the first is the overlapping wave function of psi gamma and the wave function of the vector meson. And then this is describes the dipole scattering and the target, and then do the Fourier conjugate from the coordinate space to the momentum space. Here, B is the impact parameter. I was showing the last talk. And this is the Fourier conjugate of the momentum transfer delta. Delta is roughly a square root of minus t. T means the momentum transfer of the target. For example, proton p minus and t just delta just the p minus p prime minus p. And the most important object is undescribed dipole target scattering amplitude, and also it encodes the information of the target.
And is the J psi wave function known well?
No, this is a non-perturbative process. And people usually use Gaussian or boosted Gaussian formula for the wave function of J psi or rho.
It's taken from somewhere.
Yeah, just some effective parameterization. People usually use Gaussian formula for wave function of J psi. Since this is a non-perturbative. And this is a perturbative, this is a QED process. We can calculate perturbatively.
It's like Gaussian in R.
Yeah, and we have the size R of J psi or rho of psi of phi.
Okay. So it's okay.
Yeah. And people have demonstrated that the Gaussian can describe the higher data very well already.
It's constrained from there.
Yeah, constraint from there. So it's not our model input, or we're taking from previous works.
Do you think that means that the Q and the Q bar are very close together? Or,
In R?
yeah.
Yeah, we include R here. But R should be a small size compared to the B. Yeah.
And B, I should really see that's the distance between the set of dipoles and the center of the nucleus.
Yeah. Just to show you here. We assume that this is a dipole, central dipole. There is also the central of the target. Yeah. Okay, let me talk about the N, just the dipole target scattering amplitude, since this is a very important object. First, I'll describe in the IP set parameterization. Since this parameterization is very good help us to understand the physical picture of the dipole target scattering amplitude. In this IP set parameterization, the dipole target amplitude can be calculated in this formula. Here F is proportional to the Coulomb density, Coulomb distributions at scale, and this satisfies the Diglab evolutions. And T is just the Sims function of the target. So we can see from this formula, the dipole target scattering amplitude can exercise to the spatial target spatial structure. This is described by TA, T proton or nucleus.
And RT is the dipole size, right?
Yeah, the same. Sorry, this is just this one. Yeah. No, RT is transverse. This is 3D. And we translate, oh, sorry, the same. The same.
Yeah, that is just always transverse.
Yeah. So, and let me return back this formula. For example, if the RT is very small, we can do the Taylor expansion. For example, that is proportional to the target Sims function. And then we return back to this formula. This shows that the dipole target scattering amplitude is just the Fourier transformation of the Sims function of the target. So that's why people use, for example, star people just do the Fourier transformation of the section and to the momentum space, and then they can feed the data to extract some radius or some information of the target.
But why do you write that F it depends on RT? Because in that formula there's no RT.
No, it's RT.
It's in the scale there. Oh, okay.
RT is roughly depends on scale and involved by Diglab.
I see. Okay.
Yeah. Okay, then in our calculations, we use a CGC model to describe the dipole target scattering amplitude. And in the CGC model, the dipole target scattering amplitude can be calculated from the Wilson line by this formula, the choice of the Wilson line. For example, this describing the interactions between quark and the target, and this describing the interaction between anti-quark and the target. And the Wilson line is a solution of the classical Yang-Mills equations. And with the source, rho describes the color charge density. And in the CGC framework or in the MV model, we assume that the rho is Gaussian distribution, and with the width of the G, with the width is controlled by the G square mu square. And more detailed, in the CGC we introduce a saturation scale, and the ratio of the QS over G square mu. This is a Fourier parameter in our model set. And this, in other words, this parameter controls the magnitude of the color charge and then translate to the scattering amplitude. And the QS is determined from the IP size parameterization. It's a bit technical details. Yeah, just in a short, in the CGC framework, we factorize the mu to the product of the Sims function, and the mu x depends on the built-in x only. The above two slides just want to show that exercise to the spatial structure of the target, or either proton or nucleus. So we can get information by the diffractive process to the target information. Okay. As Kong already said, there is the diffractive process. There have two processes. One is a coherent cross-section, and another one is an incoherent cross-section. The coherent means that the target state interact, or in other words, the initial state is the same as the final state. So we can get the coherent cross-section is proportional to the average value of the scattering amplitude. So it probes the coherent cross-section probes the average shape of the target. And there is another process named incoherent cross-section. It means that the target breaks apart, or in other words, the initial state is not the same as the final state. Then if we subtract the total, if we subtract the coherent cross-sections from the total cross-sections, we can get the incoherent cross-section is this formula. And we can see this formula. This proves the variance of event by event initial state fluctuations in the target structure. The average means the average of the initial configurations event by event.
So when you write correlator, let's say brackets around A, so this is when the MV model comes in, because that tells you only about the correlator, right? With what you showed before.
No.
Because you need this correlator of rows, and that so once you do this correlator from the amplitude, then you get sensitive to these correlators, and then you plug in that formula, right?
This formula just you want to show that the rho is proportional to this
No,
parameter.
but that's not row, it's
And
the correlate.
this one?
Yeah, that's correlation.
This shows you there's no local, just a local correlation. There's no long range correlations.
So, but then the model you use when you compute a correlation, like in your average A, for instance.
Mhm.
So then you have to put brackets, and then you end up with this kind of bracket of rows, and then you have and then you can use your new parameterization with the thickness function.
Yeah.
So this is how it works, right? So,
Yeah.
Okay.
Yeah, again, this average means the average of the initial state configuration.
Which is exactly the same average which is in the previous slide. That should be.
Yes, yeah.
Yeah.
Yeah, I have to think about it seriously. Yeah, and for the diffractive process, the signature, the rapidity gap, I described home already. For example, this is the target and breakup. Here is many particles in the final state, but here is a rapidity gap of the vector meson productions. And in the theoretical side, there is no net color transfer. As I described, since the final state is a color neutral object, and the initial state is a color neutral object, so there is no net color transfer between the dipole and the target. Okay. And then for the proton geometry, since this is the non-perturbative process, we use some effective model to describing the proton geometry fluctuations. For example, the protons event by event the protons event by event density fluctuation profile can be calculated by this formula. Here, this is the protons density profile is the sum of each hotspots profile, and but each hotspot has a relative weight described by pi, and the pi we sample the pi by this log normal distributions. The reason we use this log normal distribution of pi is just this can describe the LC multiplicity PP collision, multiplicity distribution in PP collisions. And we have parameter sigma that controls the weight of each hotspot or the fluctuations of each hotspot. And for the density profile of each hotspot, we assume is also as a Gaussian, and we have another parameter named BQ. BQ controls the size of a hotspot, the size of each hotspot, and also the hotspot position BI are sampled by another the third Gaussian formula. We have the parameter BQC that roughly describe the proton size. In other words, we have a parameter sigma and the size of hotspot and the size of the proton. And this is the energy density profiles with the different number of, and also we assume that the number of hotspots can be a free parameter. We can fluctuate, we can use different numbers of hotspots, and this is the energy density profile with different number of hotspots. For example, this one around is more like a round profile, and this 3, and this is 9. We can see the clearest difference between the different number of hotspots. And let me summarize our model parameters. In describing the proton shape, we have 7 parameters. For example, the number of hotspots NQ and the proton size BQC, and also the proton hotspot size BQ and the hotspot density fluctuation sigma. And we also introduce the minimum distance between hotspots, the DQ minimum.
Excuse me.
Yeah.
Can you just pause that down? So I just don't know. Where did this pictures?
Oh, this is just effective parameterization model, just a very simple Gaussian for each hotspot and add them together.
It's plotting this TP essentially
In this one,
So this is the plot
of the TP with a random sampling of hot
Ah, okay.
positions of hotspots
yeah.
and normalization.
So from the column.
It's a
Yeah,
Monte
Monte
Carlo
Carlo, yeah.
it's a Monte Carlo proton proton
Yes,
structure.
yes. You sampling this on your long representative.
Yes. And there is some noise, I believe, because that's the color charge fluctuation, right? Which is some, but they're not part.
But it's not physical.
This is and it is really an effect.
Yeah, it's because this similar. Clusters. It's called molecular dynamics.
Actually, they only put in this hotspots to have something which fluctuates.
Okay.
That's the main goal.
Thank you.
so we just let them to the free parameter. So you have certain parameter and also the overall charge, color density parameter, and also their infrared regulator M, which attend in the Wilson line here, just to screen the long range infrared physics. And also we feature the higher data, including the incoherent and coherent cross sections. In other words, we have the 3D parameter space, and we generate 1,000 training point for the model emulator, and then use the Bayesian analysis by featuring the higher data to constrain the
So
proton
this
shape.
is like your best result.
Yeah, this is the best result. Yeah, then we use the Bayesian analysis to constrain the proton shape fluctuations. This is a Bayesian theorem, this formula. Here, for example, this is the probabilistic constraints of the model parameters given the data. And this is proportional to this formula. Here, prior P is just the external constraints on the parameters, such as the positivity or range of the allowed values. For example, the probability shall be positive, the number of hotspots shall be positive. This is the external constraints of the parameters. And here, the D means the mean value of the data or mean value of the measurement, and the distance between the data and the model calculations with a given parameter set P, and divided by the model and experimental uncertainties. In other words, based on the Bayesian theorem, we constrain the model parameters by the Bayesian massive Bayesian analysis. And before I go to our result, before do the closure test, we have the 1,000 training point to train the emulator, and then we run extra model parameters and use the this model output as a fake data and use the emulator to use that fake data to constrain the parameters. For example, here red lines is this model parameters, and the black line is the likelihood posterior distributions of the model parameters constrained by this fake data. You can see that most model can be well constrained with a very beautiful peak structure, and the peak location locates at the our expired model parameter value. For example, the proton size and the hotspot size, and also small wins and also the curious nil ratio. But some parameters is not well constrained. For example, the DQ minimum is the posterior distribution is also flat. Flat means that we cannot constrain these parameters by fitting the current higher data only.
What's the difference between left and right?
Oh, that's just two sets, two different sets.
Two different.
Yeah.
But so like the NQ, you get completely different results, right?
Yeah, so this is inputting the expected NQ difference.
So the input value is different.
Yeah.
Oh.
Yeah, since the input fake data is different, so the emulator will give the different posterior distributions of NQ. Yeah, and then First, I would like to give you some intuitions of the model parameters and their effect on the higher data. For example, first one is the proton size. Going from left to right, the proton size increase. And then with the increase in proton size, the coherent cross-section dips faster, which means that since the location of the first dip is inversely proportional to the proton size square, so the larger size proton size, the incoherent cross-section will dip faster. And also the second one is the hotspot size. From the left to right, the hotspot size increase, and we clearly see that with the increase in hotspot size, the incoherent cross-section decrease, and also the coherent cross-section decrease faster. This is because with the larger hotspot size, it will decrease the fluctuation of the proton. So it will decrease incoherent cross-sections. And also with the larger size of the hotspot size, the coherent decrease faster, which means that the proton size becomes a bit faster, a bit larger. And also the third one is the infrared regulator. From the left to right, the infrared regulator decrease. We can see that with the decreasing infrared regulator, it mainly affects at the low T regions. This is because the infrared regulator, this parameter mainly controls the contributions from the large scale. So when we do the Fourier conjugations, it will mainly affect the small T regions, both in the coherent and incoherent cross sections. And also this is the overall charge color density from the left to right. The overall color charge density decrease, so it will decrease the cross sections, both the coherent and the incoherent cross sections. And also this parameter shows the hotspot density fluctuations. From the left to right, the fluctuations decrease, which means we can say that the less fluctuations mainly affect the incoherent cross sections, but have little effect on the coherent cross sections. So which means the incoherent cross section probes the fluctuations of the proton geometries, and the less fluctuations will decrease the incoherent cross sections. And also
in
this,
a sort of T-dependent way, right? It's also T-dependent, right?
yeah, there are some T dependence. For example, large effect at low T and small effect at high T. Okay. And also this is the effect of number of hotspots. When decreasing number of hotspots from 7 to 3, the fluctuations of the proton geometry increase, so it will increase the incoherent cross sections, and slightly increase the coherent cross sections when decreasing number of hotspots. And now the last parameter is the DQ minimum, which describes the minimum distance between the hotspots, returning from 0.25 to 0. There is no effect, both the coherent or incoherent cross sections. So in other words, this higher data alone cannot constrain the DQ minimum or cannot constrain the minimum distance between the hotspots. Okay, we have uploaded all the models emulated data in this website. If you are interested, you can play it by yourself. You can change one of the parameters or two of the parameters and see how they affect on the final result, both the coherent and incoherent cross sections in gamma proton collisions.
I can speak. Is one of the parameters the number of hotspots that you can adjust or no?
No, yeah.
It is. I didn't see
Yeah.
that. Thank
Yeah.
you. Thank you.
Yeah, you can check the number of hotspots and see how they affect on the result. Yeah, this website is very good, help us to build intuitions for the model parameters and their effect on the result.
So do you know how to build this website? So who did this?
This is trending, yes.
Probably
But
June.
Chun did it.
yeah, but the source code is online. You can download source code. I think
But where
just,
does it run? Where does it run? Is it you hosting it like on a computer or are you? Is it a public?
it is public, I think. I think JSCAP also have this stream rate. No?
Yeah, Jetscape hosts it, I think, on their.
It's probably the same.
Yes, I think it's the same. Just
Yeah, good.
try to borrow the code from JSCApe.
Oh, I see.
'Cause I mean, well, originally they were just running it on like some free version of Amazon AWS, but then they wanted it hosted themselves. That was a fair amount of work, like to figure out like how to make sure everything was running properly on their self-hosted server. So I was just curious what you did, but
It's same address. It's the same address.
we'll probably say running in the same place then, yeah.
Okay, yeah. And also, this is we use a real hero data. We use train emulator and input the real hero data to get the posterior distribution of various parameters. In our calculation, we found since the number of hotspots cannot well be constrained, so we use two set parameters. The red line means the fixed number of hotspots to 3, and the blue line means we let the number of hotspots is a changeable parameter. You can see this is the diagonal plot is the likelihood of posterior distributions of these three different parameters by fitting the hero data. We clearly see some parameters can be well constrained with a very beautiful peak structure. For example, the infrared regulator and proton size, hotspot size, and the fluctuations. But as I said, the DQ minimum is flat, cannot work well constrained. And the number of hotspots, for example, the blue lines, if you allow the number of spots is a variable parameter, then the likelihood distribution of number of hotspots decrease monotonically. And this is a diffractive data from HARA at 75 GeV. Here we sample the posterior distributions. We sample the parameter point based on the posterior distributions and then run the model simulations. And this is a band shows you. And the solid line is just the mean value of this model output with the parameters sampled from the posterior distributions. And it describe the data very well. And then with the parameter fixed by fitting the hero data at 75 GeV, we also extrapolate to the 100 GeV. It also works well in describing hero data at higher energies. And let me talk about something more about what do we get by fitting the hero data using a Bayes analysis. First is these three parameters, for example, infrared regulator and proton size and hotspot size. And this is likelihood by fitting the hero data. And the red line is a fixed NQ3 case, and the black line is a variable NQ case. This, we can see these three parameters are well constrained by fitting the hero data. And more detailed, if you compare to the black and the red lines, the black line has a wider likelihood distribution compared to the red lines. This is because the variable NQ will have more parameters, so we cannot well constrained compared to the fixed NQ case. And for the 2D root mean square proton radius, if we look at the peak location or the map parameters of the proton size or the BQC and the hotspot size, we can get that the proton radius around 0.6 Fermi, which is consistent with the result from the heavy anculations that you're fitting the VT-PT curvatures in heavy anculations. I think this is calculated from Juliana. Right?
Is it plus or minus how much? Plus or
Oh,
minus?
well, we only use the map parameters.
Oh, it should be small, right? Because these are very nice peaks.
Yeah. Yeah, you can get some 90% credible interval, so very small value, I think. What is the roughly estimate?
And is there a natural reason why it's not 0.84?
Because you have no reason to probe the charge density.
So what density is
This will be like
Yes.
the gluon density.
Yeah, this is the
Relevant for high energy scattering,
Uh-huh.
and that's typically a very small scale.
yeah, this
But
is
as you said it's 0.4, but this is 0.6.
Because this is the RMS radius, it's not the radius of the Gaussian. That's the square root. There's a square root of 2 in front. So the
Usually
Gaussian,
it's using RMS.
well, in the models we use the Gaussian width. Yeah, so if you want to say what is the RMS radius, you use this one. But if you want to make a model with Gaussian, then it's this divided by square root, and then you get something.
Yeah, but then that is just terminology is different, but it's the same size. Right?
Yes, depends on what you have to do with this model or what's the RMS radius.
So for example, sorry, so for example, the charge radius, which one should I?
0.84 is it's with the square root of 3 actually.
How do you define this difference?
Well, we don't really know, I guess. It's just that apparently these processes they probe shorter scales.
So this is also one of the hint of this gluon baryon junction. They're saying that if you have this picture, the valence quark, you have 3, and then the junction you have more gluons that connect through the center. Then you do this RMS, the average gluon radius that is actually smaller than the chart.
This gear is like a valence, it's like a valence point crust. And the mass is contained in the gluon center.
I mean, just simple picture, I don't know, cross, but you have 3 charge and valence quark.
Across
They
the
could be-
shell.
Because gluons don't have to do this.
Exactly. So this is actually if you have an electromagnetic probe, you can't probe the gluons. You have to probe the chart. But this probe, you probe the gluons,
Only
but not the
gluons.
chart. Only gluons, not the chart. So in principle, if you take these 2 independent information, you compare them, sort of understand a little bit where the gluon distributed.
No, but I like what you said, that it does not necessarily, it doesn't mean there's a distinct separation. It doesn't mean there's that junction and then the valence around it. It just means that the charge radius is bigger than this central core, which has gluons, which is gluons.
Wami, have you heard about this? Have you heard of this?
heard about what?
So at Hera, so when the data they used to fit it, right, this Hera famous H1 data. At the time, they have a lot of fits. And then they get this gluon proton RNS, right? It's about 0.6 Fermi. And then they said, okay, how can that be comparing to the charge radius? So then they point back to this baryon junction where they have this gluon at the center. This is sort of like a naive expectation to explain why this is 0.6 Fermi. So I just wanted to tell you that the background at Hera, that the people use this number as sort of a hint to interpret why the gluon radius is small.
Okay.
We have to do this in the discussion, because I want to see this paper. It sounds
Yeah, and also Helium community from the world give us the
Yeah,
proton
that's,
size.
that's probably different. When you want to do nuclei collisions, you absolutely need to, well, if you start from a picture where you're sort of probing the point density, then you need to smear this nucleus with some scale, because then you need a way to create density. So you just collect points, you don't create anything, you need some scale for the interaction. And although I mean that's a model, so it's not completely straightforward related to this, I would say. But there we get the same scale seems to be working well.
Yeah, but in your calculation, you result is very sensitive to your proton size, right? Very sensitive to your proton size, and you can constrain the proton size.
Yes, you can find observables that depend strongly actually on the model, the parameter that you implement. That was the result.
Yeah, even in Helium condition.
And there, from this observable, the way one can understand is that you need the scale which is close to what is found also in this other probe.
So just try and understand, is this not for single?
This is for one probe.
This is
So
a-
how this will change?
That's the point. It seems it does not change.
So it survives.
Yes, this is you sort of probe the same length scale if you do infra scattering.
So it has to, this number has to survive.
That's the I would say that's how I understand it. And
Oh,
it leads to a consistent picture of all this phenomena.
oh,
but
that can
that's all.
change.
And the details that.
So this is the same message as the incoherent JSI data. They use the Hera data to fit it, and you see the shape, it's really the same. So then you ask the free proton versus a proton embedded in.
Yeah.
That's what you did for the Lucha one, right?
No, heavy nucleus, heavy nucleus.
You did also have the nucleus.
I'm sorry, the conclusion, just finish that statement.
The size in terms of gluons, the free proton versus a bound proton are not so much.
Well, that's a strong conclusion.
For these high energy processes at least. Right? That's what you would say.
Yeah, everything.
As
depends on the
probed by,
proton.
yeah.
Everything depends on the proton,
As probed by these very high energy processes, this, there's no modification
of the size.
on the size of that.
So, yeah, my question was, should I deal with the
No worries for you, what you really, at least you want to give something to us. Let's read the point densities. Then we will play with the sizes. But what we grow are the
No, I mean, in principle, I need this for many things.
But that is under like rules.
I don't know how that would enter in your calculation.
But then you, wait, you saw the symbol.
Right,
I-
right.
So can you extrapolate that? But this number also change with energy.
That's a good
because
question.
it's
Yeah, so,
different.
so for example, in the saturation picture, they predicted this will change.
Yeah, but so if you look at the actual numbers, it's like a change from like 200 GeV, central mass energy, to 5 TeV. It's probably 0.1 Fermi, what that is in Fermi. So it's a very slow
Yeah, but you're
change.
talking about neutron skins in lab is 1.2 Fermi. So it's about the size of the neutron skins. That's about the.
Yes, but neutron skin is a difference, right? Neutron skin is a difference. Between
Oh, it's a different, but you're also talking about the difference. Talk about the radiation.
yes, but neutron skin, you take the difference of neutron minus protons. And I think whatever size is attached to the protons or the neutrons, to a very large extent cancels in this difference. So you're not really sensitive to the scale of the proton, the size of the protons.
Yes,
And then
but
you
I
can-
have also absolute values. of absolute
So if you talk on the other hand about the matter radius, for instance, then you have to include probably some correction from this size. If you're talking about only matter radius, gluon radius, of the entire nucleus,
Mhm.
but that in that case will be a very tiny correction, 0.4 Fermi, something like that. The Gaussian size.
0.4 Fermi.
Yeah, for the Gaussian, it will be 0.4 Fermi, so it's a little more.
I think it's better if you can avoid the new uncertainty of order 0.1 Fermi when you're dealing with things
Yeah,
like
yeah,
0.2 Fermi, you should avoid it.
Yes, but I mean, like, in the neutron skin is a difference.
It is, I'm not saying that this guy affects that guy, I'm saying if you're doing physics that cares about scales or 0.2
Yeah, the matter radius, for
Use-
instance, if you want to know the matter radius, then that will have some energy dependence, probably. Small energy dependence.
Yeah, we care not only about.
Yeah, if you don't care about the difference, like the sum, then yes, you have
Sorry.
Okay, thank you. Thank you for discussion. Yeah, and then comes to a number of hotspots. We see that, for example, we let the number of hotspot the variable parameter, but the likelihood distribution of number of hosts increase monotonically. That which means the seems higher data lakes like as much as number of hotspots as possible. But we look at more detailed, for example, this is a strong correlation between number of hotspots and the QS fluctuations. Let me remind you what is the QS fluctuations. In our model simulation, protons event by event fluctuations are calculated by this formula, which is the sum of each hotspot. But each hotspot has a relative weight of pi, and the pi is sampled by this log normal distribution with the width of sigma, which means the larger value of sigma will introduce the larger fluctuations of each hotspot's contributions to the proton. So there is a strong correlations between the number of hotspots and the fluctuations. And for example, if we get to the number of hotspots is 8, but with large fluctuations, the number of effective hotspots should be smaller than the number of hotspots we extracted here. Since we have the fluctuations of each hotspot contributions.
So this is why you have this tail for the likelihood of variable and Q, because you have this tail on the number of hotspots, and that can get compensated by lower QS fluctuation, right? Understand correctly.
Yeah.
So you get the same result.
Yeah. Since the larger fluctuations, but the effective number of hotspots is smaller. For example, than the number we extracted here. Yeah. So we get the same result of
This tail is due to that.
The tail in the middle block.
Yes, there's this tail on the left,
Yeah,
which is
yeah.
because you have this non-constraint on the left. Sorry, the tail in the middle.
Okay, on the left.
On the left hand of the distribution in the middle plot.
That makes sense.
Yeah.
But I'm looking at the shoulder at NQ equals 2. Yes, what is that in the plateau? What is happening there?
Yeah, this shows that the NQ1 is clearly disfavored, but from NQ2 to NQ6 to NQ8 is not well constrained. Yeah, and then in order to describe the number of hotspots more precisely, first, this is the map parameters with NQ9 and NQ3 case. For example, one of the most important values is a different infrared regulator, since this parameter controls the final structure of the density profiles. And this is the density profile of proton with map parameters of NQ3 and NQ9 case. And by eyes, we can see the clear difference of the density profile with the map parameter of NQ3 and NQ9. For example, this is a very large structure compared to the NQ9 case. And this is a proton density profile with the map parameter of NQ3 and NQ9. We also, by our eyes, we can see a difference between them. But higher GPSA data cannot disentangle these two density profiles. So in the next work, we just see them by different probes. First, this is the GPSA higher data, and with the map parameter of variable NQ and NQ3, this also gives the same cross sections of higher GPSA data, either 75 GV or 100 GV. And then we also get the row productions, since the size of row is larger than GPSA. So for example, the size of row is larger than GPSA. So row can probe the larger scale compared to GPSA. And this is the map parameters of the row productions with NQ9 and NQ3 case. For example, we can clearly see the difference of the row productions with these two map parameters. Let me remind you again that these two map parameters have no difference on GPSA productions, but we can see a difference of the row productions at Q script 3.7 or 6.6 GV. This is because the row is larger. You can see the larger scale compared to GPSA of the configurations. So the row productions can capture the difference between these two configurations. And more detailed, if you go Q square from 3.7 to 6.6 GV, the difference between blue and red line is smaller, which means go to the higher Q squares, the size of row probes is also becomes smaller. So the difference between these two lines becomes smaller to return back to the GPSA finally with very large Q square.
So okay, it's a bit fast. So when the probe is larger.
Yeah.
And you're comparing different number of hotspots.
Yeah.
When you say that 3.3 GeV in Q square, it cannot describe the data.
Just forget about data, just to see a difference.
Okay, so what do I learn?
Oh,
I increase the Q square and these two lines, the red and the blue gets closer.
Yeah, since the probe at higher Q square is smaller compared to the smaller Q square, so it will return back to the GPSA. The difference, the return back. Let me remind you, these two lines give the same result of GPSA productions. but they give a difference of row productions.
But isn't it no, sorry, go ahead.
But the scale is actually effectively the m square n q square plus q square, right? So effectively, a row, your m square is small, but then you compensate by q square. That's what it means.
Yeah.
And then it has nothing to do with describing the data, right?
Yeah, so in order to describe data, we have to maybe fine tune the parameters or introduce more effects.
So I'm trying to understand what I learned from here. So it means the scale, it's q squared plus m squared. Right? It's just effective scale.
Yeah.
And then you can use it. You can use row, but then you need to go to high q squared.
Just high Q square mean guarantee is a perturbative region.
Yeah.
You can do perturbatively. For example, Q square 0, row is very light, so it's non-perturbative process. This approach doesn't work. Yeah, and the message is that row probes a larger scale than chip size, so you can see a difference, a larger scale compared to chip size. You can see the difference between these two configurations.
The different masses, they allow you to play with the K-max variables. That's the thing.
Yeah.
Because I mean, these plots that you're showing for the two are completely different in scales of the axis.
Me as well.
Yeah.
Yeah. Just to see, I just want.
Cross section.
No, this is a
Row
cross
is
section.
much higher.
Yeah, that's the section is much higher.
Yeah, but they care about the shape. They don't
Yeah.
care about the cross.
Yeah, we care about difference between these two lines.
I would say not as strong, but if I could go to that very low value of t, and I would zoom in the J psi curve, would I see the same difference? Probably.
You mean zooming low?
Yeah, zoom in
This is
there.
already 0, very close to 0. We cannot
Yeah,
go
but
to
the
lower.
wide range is like completely. Okay, well, it's just a bit.
I think that's a good point. I see it.
I mean,
Basically, the scale is different, and if you zoom in, maybe the difference between the red and the blue is.
Yeah,
also-
maybe you can see a ratio.
It's a matter of ranges, basically, the way I see it.
But I guess the absolute difference, I think it's larger in the row.
Yeah, absolutely. We can see a ratio even.
Exactly, that would be more
more transparent.
understandable.
Yeah. But you can see also the difference shall be larger in row productions. And also we connect back to the Hebbian collisions with these two map parameters. We use the map parameter on Q3 and then Q9 shown here in red light collisions and compare it to the Alice data.
Is this published?
No, it's not published. We are preparing
I
this
don't
one.
remember.
Yeah, this is, for example, this is configurations of map parameters within Q3 and Q9. We can see a difference by our eyes, and also flow data can also see the difference. For example, the multiplicity distribution of charge multiplicity in ladder light collision and LC, and we use a different map parameters and run the hydro and run the humidity. Other parameter is the same except the different parameters in the initial state.
So we can forget about MQ9, right?
Oh, well,
I mean, if I look at the plot on the right, it's terrible.
yeah, it's terrible, but yeah, well,
By the way, on the right,
You're keeping everything fixed here.
It's a
You're
bit
not
busy, so
retuning
which-
all the other parameters, right?
I guess.
So it doesn't really mean,
yeah, which curve is which curve on the right?
I don't know.
oh, here the solid line means in Q3 and the dashed line is in Q9, and the different colors means different observables.
Yeah, where's the dash line? I can't see. the
Oh,
dash.
It's not really there.
Yeah, this is dashed line.
Oh, okay.
And
But
then,
what Matt was saying is very important as in this calculation. Are you just changing NQ and nothing else, or did you actually?
we just changing the map parameters in the atglasma, not only in Q, but also M and some.
Then it's unique.
Yeah, and also the
Yeah,
hydrodynamic is the
you said
same.
they kept it fixed to the map parameters, right? So you only change NQ, all the other parameter value is fixed.
That's what
No,
you're
we
saying.
use these two state
No, they're
parameters.
different.
Oh, I see.
These two state parameters can describe the chip size hydrodata well.
Equally well.
Yeah, you see here.
Okay.
But I mean, what about these hydro simulations have a bunch of hydro parameters? Well,
Hydro parameter is the same. in these two
they're the
lines.
same, yeah.
And then
They're
it's-
not retuned.
Yeah, it's not two.
Can you explain the glass more? What's the main reason?
Oh, just
That's a good question.
Yeah.
I want to hear the answer.
this one. just what do you say, plasma.
Well, just the classical,
That's a great test.
classical young wheels evolution, right?
I mean, it's, there's a lot of ingredients, right?
The interest.
A lot of
It's like a
ingredients.
plasma and.
Yeah, IP plasma has a, yes.
But she asked only glass.
Oh, I thought you said IP plasma, the whole model. Oh, okay, plasma is simpler, yeah.
Just like color glass condensate, and then
That's
there
really
is
glass.
So you have a
Classical
condensate of some kind?
Yeah.
We were talking about condensate.
No, but it's not that one. I mean,
What
you should
is
take
the
it like
plasma?
Yeah.
real context.
We're not very good at naming things,
No, so
but
you can think about the glass mites like, you have some colored tubes. So basically you have a color, you have a nucleus. And then in this nucleus, if you look at the transverse in these directions, there are many color domains in this nucleus. And in this color domains, you can form like this local, like a density. And then they sort of map it out like when these two pancakes pass by and they drag this, it's like a tube, like a color tube.
Just like some gluon substructure.
Right, so it's kind of like a localized gluon domains. That's
But in practice, what's really important is that
G is for blue.
It's like
A
Yeah.
plasma.
yeah.
Gluon
G for
plasma.
gluon.
no, it's actually like plasma and glass. That's
yeah, I think it's the glass,
To
color
the
glass.
condensate, I think you need a little bit more, but then just for plasma, the picture is just
That
you
was
have the
really,
local domain of this.
So what's
color.
important is that they have this very highly occupied gluon field, and then what's really easy is a semi-classical approach where the evolution subsequent to the crossing is just a classical evolution, basically, where you set up like chromoelectric and chromomagnetic fields and you roll them in classically for some time. And this gives you like the initial instance after the condition. So this is the plasma evolution. It's a classical young evolution. You can write it down and solve it numerically.
Why there's a G there when you say glass?
Because they say glass, I don't know exactly why they use there.
So, okay, so this goes back to the naming, right?
It's just naming, right?
No, no,
It's not at all like the real glass.
No,
But that was
The
not-
I'm not sure, I disagree, because
It was very universal. What does my need this?
so color glass condensate, the name comes from the property of like a glass, because it's a very chaotic system, that on a long time scales, it looks like a glass. And then short time scale is like a liquid, right? So in principle, the name of this color glass condensate comes from, at this initial stage, right, you sort of like have a very gluon densities. At the different time scales, this is sort of an analogy to the glass. So that is why the glass is in the picture, and gluon, of course, everything is gluon dominated, and condensate is by the saturation. So the three words actually correspond to three properties.
Okay.
But did you make a typo in your statement? On long time scales, glass is a liquid. On short time scales, it's a solid.
Right.
No
That's right. Yeah. I misspoke.
It's a length scale or time scale.
Yeah, I mean, the name isn't that
If it's cold,
good.
But
It's cold?
I think it depends on temperature.
Yeah, but the name of that
Don't take it, don't
is,
take the name so literally.
but that is where, but that is a historical,
Yeah, just,
why the name is.
That's the name is from Latu.
The name?
Latu University.
Yeah, and Larry next door.
Yeah.
creation is always- this is actually-
I think Shuriak was the CGC.
Sure. Yeah.
No,
Sure.
Didn't he invent the color glass
I
condensate
think it's
name?
entirely Larry McLaren.
Was it later? Oh, okay.
How long ago? How many years ago? 40.
Oh, wow.
A good name. Okay, then this is the pillar hydro result, and also with the map parameters of Q3 and Q9. This is the central dependence of charge multiplicity in pillar ALC, and we see that there is a clear difference of the charge multiplicity with these two map parameters. This is the VGPT correlations in periodic relations at ALC with these two map parameters and run hydro and run hydro cascade. And short message is that similar to lateral collisions, pillar flow data also favors the Q3 case as well. And also on the other hand, we see very difference between of the VGPT correlations between these two map parameters So this is very promising observable, help us to constrain the number of hotspots and constrain production even better. And so in the future, we would like to explore the more experimental constraints by using the HARO and the LC, light and appear data to constrain the proton shape in the future.
But why is this N charge so small? That should be much higher.
This is a middle amplitude.
There, just 40 at top village energy.
This is Alice cut. We only middle amplitude.
We can discuss it. I think there's something weird because it should be like factor 3 higher.
This is PLED, this is
Yeah.
experimental quantity.
Yeah, but the NDA.
So you may see the centrated dependence at the very central collision is around
This is PLED, it's not
40. This is middle.
Yeah, but like that is 2000. Pilet should be 100. I'm pretty sure. We can check.
Yeah, this is pillar. And also, we also have another test, just a fixed NQ case, and then train the emulator and use HARO data to maybe to try to extract something with a fixed NQ case, which means we assume proton has no substructure or proton only has one quark, valence quark. But in this way, the emulator will give you very insane posterior distributions of these parameters. For example, M and the proton size is very insane values. And even in this way, we run the model with the posterior distributions sampled from here. We still cannot describe the coherent or incoherent data with a fixed NQ case. In other words, Bayes analysis with fixed NQ case cannot extract the parameter set to describe the HARO data. And this conclusion is also consistent with the Havian collisions, as I shown before, which means the round proton will greatly underestimate the flow data compared to the fluctuation proton case. So in these two data also tells us that proton has a substructure fluctuations. And then I'll go to the next topic, just accessing nuclear deformations at small x. This has been well discussed in previous talks. This is a generalized reduction profile of nuclear shape. We have we use this parameterization for the R. They have the different deformation parameters. For example, the beta 2, gamma, beta 3, and beta 4. And the different deformation parameters control the different shape deformations. For example, the beta 2 behaves like elliptical shape, and the beta 3 is ocupal shape, and the beta 4 and gamma. And we sample the nuclear position inside the nuclear based on this generalized precession distribution. And we use the same diffractive process to prove the nuclear geometric deformation or deformed gluon density distributions by the diffractive process. This is the first result of the gamma uranium collisions. We systematically change the beta 2 values by hand from 0.0 to 0.82 and 0.5 in uranium. And we see the difference in the coherent and incoherent cross sections. We can clearly observe that the low T regions, different beta 2 values give a huge difference of the incoherent cross sections in the diffractive process. And this is because the uranium has a randomly 3D rotation, and with the non-zero beta 2 or non-zero deformations, this randomly 3D configurations project onto the XY plane, and then the projections will have event by event grid fluctuations. And then these fluctuations will translate into the incoherent cross sections. And since the beta 2 controls the deformations at a large length scale, and then when we do the Fourier conjugation to the momentum space, it translates into the small T regions. So that's why we see the huge difference at low T regions with different value of beta 2s. And this is the configurations of different 3 independent events with the different with the beta 2 of 0.5. We can see the different configurations in the XY projections. And also, we not only beta 2, we systematically change the beta 2, beta 3, and beta 4, and see the difference in the cross sections. And it's showing here as a blue shadow region shows the difference where they manifest. For example, this beta 2 manifest at very small T regions around 0.01 GeV square, and beta 3 is middle intermediate T like 0.01, 0.02, and the beta 4 is a bit higher T regions between 0.2 and 0.3 regions. And this is because different deformations affect the fluctuations at a different length scale. For example, beta 3 controls length scale is smaller than the beta 2, but larger than beta 4, and the beta 4 is most. And also, the same process we go to the momentum space, translate to the different T regions. And if you look at the coherent cross sections and the different deformations, you see that the location of the first dip in the different deformation parameters is the same. In other words, the different value of deformations do not affect the location of the first minimum of the coherent cross sections. And let me remind you that the dip of the first minimum is inversely proportional to the size of the square. So in other words, different deformations will not affect the overall size, overall radius of the nucleus. And since the different deformations affect themselves at different T regions, so in the future, we will train the emulator with the diffractive result by our model. And then if the data have some measurement, we can use the data and use the trained emulator and with the input data to constrain the resection deformation parameters of this neuron or even other nucleus. And also, if we just in the previous slides, we mainly focus on the low T regions. If we go to the higher T regions, for example, the above 3 lines with the different beta T, but all we have the subnuclear fluctuations. The last line is a black line here, beta T is 0.02, and in this line we do not include the subnuclear structures. You can clearly see that at the low T regions in this gamma I collisions, the coherent cross section at high T regions in this gamma I collisions will see a difference of the subnuclear structures. Since this is a very shorter length scale difference, so it will translate into the higher T regions. So the low T mainly affected by overall geometry deformations of the nucleus, and the high T is sensitive to the subnuclear fluctuation inside the nucleus.
That's very impressive. So basically you see fluctuations on all scales.
Yeah. And this is into the large scale, and this is to the small scale, even inside subnuclear structure.
So that is the curve that describes the star data.
Which data?
The star data, the tail.
Just high T region.
Yeah, right. The T that describes it up to 2 GeV.
Okay, then in order to estimate whether one goes from low energy to high energies, whether this effect will be washed out, we run the G-walk evolutions from the large X to the small x. The picture of the G-walk evolution just, for example, this XP is Pomeroy X or Bjorken X. This XP determines which scale you can see the target, or which scale you can see the proton or nucleus. And the G-walk evolution, the physical picture of the G-walk evolution just it integrates the intermediate X as the source of the small x, and then step by step run the renormalization group equations. And technically, we run G-walk evolutions. We involve the Wilson line with energy or rapidity according to the Landry equations in the color space. And in these Landry equations, we assume the random noise is Gaussian, or in other words, we just truncate it into two-particle correlations. You can see more detail in the backup. And as I said, the general picture of G-walk evolution just integrates the intermediate X belongs as a source of the smaller X, and then running from the larger X to the small X. And this plot shows the coherent and incoherent cross sections at XP to 10⁻⁻⁴ 10 to the minus 5. The previous one is 10 to the minus 3. It's 2 orders difference. So with 2 orders difference, we still can clearly observe difference with different beta 2 parameter, beta 2 values. In other words, the gene work evolution does not wash out this effect when going from larger x to small x, or going from low energy to high energies.
But in practice, this revolution only changes sort of these blobs that you had in the nuclear. This thing, right? That's where that's why it plays a role.
Yeah.
So it's only there that you is affected to gene evolution.
Yeah. For example, this is nuclear configurations of uranium with same initial state, this initial state, and we run gene work from 10 to the minus 3, 10 to the minus 5, 10 to the minus 4, and 10 to the minus 5, and even 10 to the minus 10. You can see the configuration, the gluon density increase will go into a smaller x, since you see the nuclear at a much smaller scale, so you can see more gluons. But overall geometry shape is not changed. That's what gene work evolution tells you.
But we won't be able to see even 10 to the minus 5.
Oh, well, it's different.
Oh, but it doesn't do anything anyway, so you don't just probe this.
But just to see how the how the evolution tells you. Yeah, and the concept, this is the integral incoherent to coherent ratio. It cancels the overall normalization and also the uncertainties from the wave function. Since the wave function, so for example, the wave function of vector meson is non-perturbative, and different choice of the wave function of vector meson mainly affects the overall shape. And if you calculate this ratio, it will eliminate these uncertainties.
So is that true that the wave function cancels in this 2 cross section? Because that's my intuitive expectation, but does that mathematically actually cancel incoherent versus coherent?
Yeah, at least people have demonstrated different choice of wave function do not affect the slope, but only the overall magnitude. So if you look at the ratio, so this overall effect cancel.
So this is sort of studied.
Yeah. And also we choose different beta 2 parameters from larger x to small x. The difference between different lines are still here, which and for the one hand, the incoherent to coherent cross-section decrease when going to a smaller x. This is because when goes to a smaller x, more gluon will emerge, and the nucleon on target becomes smoother. You can see, so the fluctuation shall be decreased, or the increased speed of the incoherent cross-section is smaller than the increase of the coherent cross-section. That's why this ratio decreases when going to a smaller x, but the difference between different deformation parameters is still there. So in other words, again, the gene work evolution does not wash out the difference between different beta 2s. As shown here, the overall geometry is still here when goes to from large x to small x. And then we also studied the neo 20 and oxygen 16. The configurations of neo 20 from Giuliano, and also for oxygen 16, we use 4 alpha clusters, and this is a coherent. This is a diffractive result. Here we use neo 20 is pin bowling ball shape.
Well, one's a bowling pin and one's a bowling ball, I guess.
Yeah.
Bowling is ambiguous. Saying bowling.
That's what I put in my slide.
They're both bowling.
If you
Sorry, go on.
do oxygen neon, you're playing bowling.
Yeah, and then we also tried other shape of Newton is a spherical case, and also oxygen 16. For example, solid line, the difference between the solid line and dashed line captures the difference of the deformation of Neo 20, and the difference between the solid line and the point line shows the difference between Neo 20 with bowling ball shape and the oxygen 16. And also the incoherent cross-section also captures the difference of the Neo 20 with bowling pin shape.
But do you understand why the oxygen coherent curve has a slope which is less steep than the neon?
Because it's small.
It's
Yeah.
the size, right? It's larger size, steeper slope.
I mean, they're conjugate. the slope, if you look at gold,
Very
it's like
good,
super
very-
steep.
Because the minimum is shifted towards the left.
Yeah.
Very good.
Yeah. Since the neutron is only 16 and the 20, so it's larger compared to oxygen. And also the ratio is 2.5 difference compared to oxygen 16. And in future, if the ELISA can measurement measure this, it will help us to understand the geometry of neon 20. This is very interesting. People like this way.
Does neon 20 have 5 alpha clusters or no?
Yeah, some are neon 20 sounds like oxygen plus another alpha
So
cluster.
like, yeah, I don't know if it should be really seen that way. That's really, I don't know.
You don't know if it's distinguished into 1 and 4?
I don't know, if, let's say, yeah, it really looks like it's like an oxygen and an alpha, but I don't know if it's really that sharp. And I would be a little careful with just bringing that.
They look like interaction clusters.
Yes, but
They're not completely
it's also very elongated. So it's
in the ground state.
the ground state. This is the ground state.
Because this shapes, you know, they can be very different.
Excited are even more weird.
Like there is famous quartz in carbon.
Is that an excited state?
It's yeah, it's inside.
And it's like this,
It looks like this in carbon. And in the ground
So-
state.
We should move on.
Okay,
We're on like overtime already.
But they're almost done.
Let's try to at least get to the.
which is
the slides.
isobar.
Mhm.
Isobar has different deformations, and this is also to study the same effect, but if you find the background in isobar is not identical. There's some difference. One of the most important things from the deformations of isobar. So we systematically change the deformations of isobar. And more detailed in the calculation, we impose the minimum of between nucleus. Between nuclei, we impose a minimum distance between nucleus. Technically, when a nucleus is added, and if it violates the minimum distance criterion with one already sampled nucleus, so we just resample it at the most angle, and so keeps the distribution of radius and polar angle unchanged. So in other words, we want to impose the non-zero de minimum, we have to assume the gamma is 0. But if on the other hand, if the gamma is non-zero, we have to choose, we have to set the minimum is 0. And this is the incoherent ratio of isobar with different cases. For example, from case G to case 6, there is only 5% difference. This difference is also close to the other star measurement is around 4% difference. But if you look at black lamp, the case 1 and case 6 is around more than 10%. And we found that this difference mainly comes from the de minimum, which in other words, the 0 de minimum has a larger density fluctuations, so it will enhance the incoherent cross sections. So in the future, we measure the incoherent cross section ratio to help us to constrain the de minimum between nuclei.
Wait, sorry.
Yeah.
What has anything to do with the left and the right hand column?
Oh, just to see the magnitude.
Yeah,
Nothing at all.
Yeah.
Pretty much nothing.
no, but then you can't compare two things that they're completely different.
Yeah,
I mean, just coincidence is 5%. Do you even know like what those quantities on the right hand side is super complicated ratios over ratios over ratios.
Yeah, I know some double ratio.
I really suggest don't use the right hand. It's gonna, if I'm the referee, this will be a terrible idea.
Because there's no information.
Yeah, the point is also that this observable will show.
No, because this observable showing 5% has nothing to do with the right hand side,
Oh, oh.
right?
Yes, but even just different observables are not related. I think.
Yeah, but you're measuring completely different correlations.
Yeah. Just to see the difference between this isobar around 5%.
My friendly reminder, just
Okay,
No,
thank
don't
you.
do that.
And also, I mean, there's one like more important thing is that these are 20 to 50%, which means that you are basically, I think in this ratio, no longer sensitive to deformations, which is what you are actually showing there. So there you only see some scheme effect of the ruthenium, and so it's that is the thing that probing something which is
yeah, but why would the charge dependent correlations of this relatively bent plane scale by V2 scale by these things will be sensitive to the deformation in 20 to 50%.
It's not, that's the point. It's not,
Right.
it's just sensitive to some scheme, basically.
Nobody knows what it's sensitive to, but it's definitely probably not.
So
sensitive
yeah,
to
it's
the
not,
left-hand side.
you could just show probably the plot of Chunjan and Zhangyong where they do V2, V3.
Mhm.
That's more meaningful probably.
Okay. Okay, thanks. Comes my summary. Okay, since time is up, I will not read it. Okay, thank you.
Thank you.
Nice stuff. Any immediate questions before the discussion? Or I'm sure we'll have plenty to discuss also in a couple hours. So maybe just go to lunch and see you at 2.
Back to the neon plot. Because there is the clustering. Oh, it's not really clear here.
That's my.
Oh, but this is a very small.
Not that